Good morning, friends. We'll start API 571. High temperature corrosion. Damage mechanism oxidation. O2 reacts with CS, carbon steel, and other alloys at high temperature, converting metal to oxide scales. All carbon steel and low alloy steels, all 300 400 SS, depending on composition and temperature. For CS, significant above 1000 degrees Fahrenheit. And SS above 1500 degrees Fahrenheit. General thinning. So equipment operating above 1000 degrees Fahrenheit, that is the main cause, or 1500 degrees Fahrenheit. And CS oxide scale 300 SS thin black scale. UT higher temperature measurement monitoring of operating temperature. Chromium is more resistant to oxidation at high temperature. Also silicon and aluminum. And surface scaling. Sulfidation. Sulfur compounds react with carbon steel and alloys at high temperature. Presence of H2 accelerates the corrosion. So all Fe base metals, inclusive 300 400 SS, nickel-based alloys, if chromium content is less. Copper at lower temperature, carbon steel, then carbon steel. So iron-based alloys, sulfidation occurs usually above 500 degrees Fahrenheit. Uniform thinning or localized corrosion or a high-velocity erosion corrosion. Piping and equipment contains sulfur at high temperature, FCC, crude, vacuum, boiler, high temperature, where sulfur at high compression is present. A high percentage is like high component. Uniform thing, localized sulfur scales depend on alloy corrosion and steam, velocity of, and presence of contaminants. Process condition monitoring. And for increase in temperature. And sulfur levels, temperature monitoring. UT and profile RT for thinning, PMI for alloy component check for any mixing of sulfur. Upgrading to higher chromium alloy, constructing with clad or steel solid 300 400 SS. All diffusion treatment for low alloy steel sometimes reduce solidification rates, and scaling, high temperature solidification. Carburization. Carbon is absorbed into the material at elevated temperature while in contact with carbonious metal or carburizing environment. So carbon steel, low alloy steel, 300 400 SS, cast SS, nickel-based alloys with significant iron content, alloy 600 and 800 HK HP alloys, typically above 1100 degrees Fahrenheit. provided exposure to carburizing environment or carbonious material and its susceptibility. Loss of high temperature, creep ductility, loss of ambient temperature material properties, toughness, ductility, loss of weldability, and corrosion resistance. Fire heater, cookers, unit, catalyst reformers, ethylene pyrolysis, and steam reformers, decoking cycles. Depth confirmation by metallography, increase in hardness, loss of ductility, volumetric increase, increase in ferromagnetism of some alloys, formation of metal carbides depleting surrounding matrix of carbide forming element. Initial stage is difficult if process side accessible hardness and in situ metallography, destructive and magnetic based techniques, ECT, determining increased level of ferromagnetism, magnetic permeability are useful to paramagnetic material initially austenitic advanced stages RTUT. Alloys with strong oxide layer or sulfide film formers, silicon and aluminum reduce carbon activity of environment through lower temperature and high in oxygen and sulfur partial pressure. Adding sulfur in small amounts into process streams of steam, gas crackers of olefin and thermal dehydroalkylation units, metal roasting, severe carburation. Metal roasting. Form of carburation with isolated localized fitting in process of steam containing carbon and H2. Low alloy steel 300 SS nickel based alloys, heat resistance alloys. Currently no metal which is immune to MD at all conditions, generally 900 degrees Fahrenheit to 1500 degrees Fahrenheit. Increases with increase in temperature, form of carburation with isolated localized heating. Fad heater tubes, thermowells, furnace components, catalytic reformers, coker units, GT, Myoc Reforia outlet piping, thermal hydroalkylation furnace, and reactors. Low alloy steel uniform wastage usually in small pits with crumbly residue metal oxides and carbides. In SS and HS, high alloy steels. Local attack with deep and round pits. For heater tubes, compression wave, UT, RT, pitting, and wall thinning, visual inspection, filtering of cooled reactor. A furnace effluent may yield metal particles up upstreams. H2S layer forms protective sulfide layer to prevent carburization. All diffusion treatment to base metal may sometimes reduce catastrophic carburization. The next is fuel as corrosion. Isolated high temperature wastage of material occurs when contaminants of fuel form deposits and melts on the metal surface of fired heaters, gas turbines. All conventional alloys used for process heaters and boilers are susceptible various melting point temperature depending on type of service and contaminants. 4121 resulting molten salt slags dissolved surface oxide enhance the transport of oxygen to the surface to reform the iron oxide at expense of tube wall or component. So fire heaters, gas turbine, burning VA and NA contaminated fuel oils or residue in fired heaters. Heater tubes sometimes not effective to skin temperature less than threshold temperature of slag, but hangers and holders are affected. Corrosion slag-like appearance. Chrome 100 to 1000 MPI. Corrosion 100 to 1000 MPI, alligator hide appearance for water walls, circumferential grooves. Refer page 121. Visual slag removal and grid blasting of water wall tubes and UT for thickness measurement. Blending and charging fuel sources, minimizing contaminants. Burner management, reducing flaming impediment and localized hotspots, injecting special additives into fuel. 50 CR 50 Ni are resistant. Hot corrosion, hot ash corrosion, molten salt corrosion, oil ash corrosion, coal ash corrosion. Circumferential cracking in water wall tubes is similar to thermal fatigue aggravated by a corrosive environment. Nitriding. Formation of hard brittle surface layer on some alloys due to exposure to high temperature process containing high levels of nitrogen compounds such as NH3 or cyanides under reducing conditions. So carbon low alloy steel 300 400 SS nickel based alloys are more resistant. Begins above 600 Fahrenheit and severe above 900 degrees Fahrenheit. So loss of high temperature keep strength, ambient temperature make mechanical properties, toughness, ductility, weldability, corrosion resistance. And steam methane reformers, steam gas cracking, olefin plants, and NH3 synthesis plants. Dull dark gray appearance, initially by metallography only. High hardness at advanced stage, increased volume of 12% chromium low alloy steel, crack flakes. Dull gray surface, hardness testing 400 500 HP. Nitriding layers are magnetic. ECT. Change in 30-80% nickel, 30-80% nickel is usually not practical to modify process conditions to reduce into partial pressure or lower temperatures. Carburization and metal dusting. So then comes environmental assisted cracking. Chloride SCC. Surface initiated cracks caused by environmental cracking 300 series SS and some Ni-based alloys under combined action of tensile stress temperature, aqueous chlorine environment, the presence of dissolved oxygen increases propensity for cracking. All 300 series are highly susceptible. Carbon steel, low alloy steel 400 series are not susceptible. Usually occurs above 140 degrees Fahrenheit. Increasing temperature, increased susceptibility, cracking stainless steel 300 series components, water cooled condensers, and in the process side of crude tower overhead condensers drain in hydroprocessing units are susceptible during startups and shutdown if not properly caused. Surface cracks on process side or extremely under insulation, no visible signs of corrosion. Branch and crest cracks appearance. Intergranular cracking sensitized SS300 brittle appearance of fracture surface. Visual PT phase analysis ECT fine cracks in PT after special surface cleaning methods UT not RT unless cracks are all advanced stage. Duplex nickel base when hydrostating use low chloride content and allow to dry through thoroughly and quickly coating under insulation. Avoid design where chlorine can deposit or stagnant. SR of 300 SS, caustic SSC EASSC. Now corrosion fatigue. Cracks develop under the combination effect of cyclic loading and corrosion often initiates at stress concentration such as pit in the surface can initiate at multiple sites. All metals and alloys. Cracking initiates concentrations such as pits, notches, surface defects under corrosion. Rotating equipment where galvanic couples between the impeller and the pump shaft were pitting or corrosion deaerator and later 80s cycling boilers. Fatigue fracture brittle, those most often transgranular as the SSC but not branched. Then propagation of multiple cracks, lethal plastic deformation, rather page 4135, UTMT, deaerator WFMT, cycling boilers, box trace. Coating inhibitors minimize galvanic corrosion resistance. Deaerator proper feed water and condensate chemical control. PWST smooth grinding of weld reinforcement, cycling boilers, slow startup and water chemistry, mechanical fatigue, corrosion fatigue. Caustic SSC. A form of SSC characterized by surface initiated cracks that occurs in piping equipment exposed to caustic, primarily adjacent to non-PWSD welds. So carbon steel, low alloy steel 300 SS are susceptible. Increased caustic concentration with decrease in temperature, increase in likelihood of failures. Function of caustic concentration, metal temperature and stress levels. So equipment handling, caustic H2S. Mercaptan removal units. Okay. Acute user caustic of neutralization in sulfuric acid alkylation units, HF alkylation units. But typically propagates parallel to the weld adjacent to base metal and also weld deposits has spider web small cracks, intergranular as welded CS carbon steel fabrication has very fine and oxide filled cracks. FMT, ECT, RT or ACFM surface prepared by blasting is required. No PT for scale filled cracks. UT, SWUT, AET for crack path. PWST, carbon steel, consider SR at 1500 degrees Fahrenheit, 300 series little advantage over CS and NI base alloys. Most resistance avoid steam out of non-PWST. Where required water wash before use LP steam for short periods. Proper design. Operation of injection system required to ensure caustic is properly dispersed before entering high temperature crude preheat system. Amine cracking and carbonate cracking. The ammonia SSC. Aqueous streams containing ammonia may cause SSC in some copper alloys, Ca carbon steel, and anhydrous ammonia. Some copper alloys in aqueous NH3 and or NH3 compounds, carbon steel in anhydrous NH3. Any temperature for copper pH greater than 8.5. Residual stresses, any temperature for steel, anhydrous NH3 with 0.2% water cause cracks in CS. Copper zinc alloys, tubes, He. NH3 is present as process contaminant in some surface or may be intentionally added as an acid neutralizer. Carbon steel NH3 stage. refracting in some low alloy refining process. The surface breaking cracks may be bluish corrosion products. Each tube few single or highly branched cracks on surface. Cracking can be either transgranular or intergranular, depending on environmental and stress level for carbon steel, non-PWST, and has on the welds. For copper alloys, monitor pH and NH3 of water draw samples. Assess susceptibility of copper alloys, HE tubes for ACT, and visual inspection. Rolled area is highly susceptible for carbon steel WFMT belts inside tanks. Exterior UT shear web AET, acoustic emission testing. For copper alloys, copper zinc alloys show improved resistance as zinc content decreases less than 15%, 1910 copper nickel, 70-30 copper nickel are nearly immune. Plus SSC in steam service controlled by ingress of air. 300 SS NIBST alloys are immune. For carbon steel PWST addition of water to NH3 0.2%. So weld hardness less than 2 to 5 BHN prevent ingress of O2 in the storage facility. Liquid metal embrittlement. The form of cracking that results when contained molten metal come in contact with specific alloy is sudden and brittle in nature. Carbon low alloys, high strength steels, 300 SS, nickel base alloys, copper alloys, aluminum alloys, titanium alloys. Temperature above the melting point temperature of alloy. Susceptible alloy 300 series SS, zinc, molten metal, copper alloys, mercury alloy 400, mercury, aluminum alloys, mercury, high strength steels, cadmium and lead. So liquid metal embrittlement occurs in very specific combinations or combination of metals in contact with low melting point metals, high tensile stress. During fire, molten metals may drop into or contact with susceptible material. LME couples SSC 300 rub with galvanic steel in refineries. HG in crude oil can condensate embrittling brass, alloy 400, titanium or aluminum X components. Low melting element aluminum components has occurred in the cryogenic gas plant components compound during to condensation of liquid mercury. So brittle cracks in otherwise ductile material by metallography, intergranular cracks filled with low melting point metal, spectrography to confirm molten metal precipitates or pieces. So MTPTRTHE tubes to locate mercury. Deposit inside because the high density. Protecting material substances from coming into contact with the low melting metal once cracking from LME was initiated. Grinding out the affected area is not an acceptable fix. LMC nickel sulfide eutectic that forms at the 1157 degrees Fahrenheit. Hydrogen embrittlement. Loss of ductility high strength steels due to the penetration of atomic hydrogen can lead to brittle cracking. Carbon steel, low alloy steels, 400 series SS, precipitation hardenable pH SS and some high strength nickel based alloys. Effect of pronounced from Ambient temperature to 300 Fahrenheit, decrease with increasing temperature, not likely above 160 or 100 degrees, 180 degrees Fahrenheit. H2 in critical concentration strength level, microstructure stresses above threshold, refer page 152. CS piping and vessels in wet H2S service in CC. Hydroprocessing amine sour water. And HF alkalination units, storage sphere more often made with slightly higher strength, high strength bolts and springs greater than 150 ksi tensile strength. Absurd S2 during electroplating and crack chromium moly vessels in hydroprocessing units. A cracks at weld size exceeds to 35 bhn. So surface breaking initiate from surface, location high residual and triaxial stresses, brittle fracture. In high strength steels, cracking is often intergranular. Surface cracks, MTPT, WFMT, UT, nor no RT is not sensitive to HC cracks. Hydrogen in embrittlement. If sources of H2 is low temperature aqueous environment, H2 blocks can be monitored with special instrument. Depend on source of H2, alloy composition, heat treatment history, low strength steels and PWST. To improve ductility, use low hydrogen dry electrodes. Bake out metal 400 degrees Fahrenheit or higher to diffuse hydrogen is expected. Heavy wall vessel requires control, shutdown and startup procedures to control pressurization sequence, apply lining, cladding to preheat surface H2 reaction into corrosive aqueous reaction, H2 flaking, underweight cracking, delayed cracking. So H2 is assisted cracking, HIC, and SU stress cracking, H2 stress corrosion cracking in HF. Okay, we'll stop here. Next time we'll start this one.